Section 4.7 talks about improper integrals. Consider the integral from 1 to x of the function 1 over t squared so I'm gonna make that not to scale a bit. You know what, let me take that one out. Here, the graph looks something like this. Come on. Here we go. And if I would like to integrate this from 1 to x, assuming this is t equal x, this is t equal 1, we're looking really at this area. So I know how to integrate this. This is really the integral of t to the negative 2 dt. So that is, add 1 to the power, divide by that. So the area is 1 over t evaluated from 1 to x. Plug x in, plug 1 in, and there it is. That's the actual area. Well, if I let x equal 1, I'll get the area to be 1 over 1 minus 1, which is 0, and that makes sense because the integral from 1 to 1 of any function is 0. If I let x equal 2, so if I stretch this to 2, then the area would be 1/2 minus 1, which is negative 1/2. Okay, I messed up. This is negative. I forgot to put the minus there. So there it is. It's negative 1. There we go. Again, this is negative 1 over t. So negative 1 over x minus a negative 1 is a positive 1. I was going to say, how could area be negative? So if I take, so this is negative, this is positive. If I let x equal 2, then I'm looking at negative 1 over 2 plus 1, which is 1/2. If I let x equal 5, so if this x was actually 5, then the area would be 1 over 5 negative plus 1. That would be 4 over 5. And if I want to find the area from 1 to infinity of 1 over t squared dt, so if I let this x approach infinity, meaning I'm finding all of this area all the way, then that's going to be the limit as t approaches infinity of my integrand, which is negative 1 over x plus 1. As x approaches infinity, this will approach 0, and the area under that infinite curve will be a 1. So it's improper because I'm integrating from 1 to infinity. I'm going to run this all the way to the right. That whole area will turn out to be a 1 in this case. Similarly, if I look at example 1, I want to integrate from 1 to infinity. That's not normal. We normally don't integrate to infinity. Infinity is not a number. It's something we made up. So there we go. If I look at the graph of 1 over x cubed, well, that looks like this. And if I want to integrate from 1 all the way to infinity, I want to find all of that area. Well, the fact that this is not a number, that's where the improper comes in. Normally, it's the integral from a to b, in which a and b are actual numbers, real numbers. So here what we'll do, we'll integrate ignoring the limits, that is x to the negative 3 dx. That is, add 1 to the power, divide by that. Evaluate from 1 to t, and we're going to take the limit as t approaches infinity. So that would be the limit as t approaches infinity of, plug that in, that's negative 1 over 2t squared, minus, plug 1 in, and negative 1 over 2 times 1 squared, because this is actually negative 1 over 2x squared. So this is the limit as t approaches infinity of negative 1 over 2t squared plus 1 over 2. As t approaches infinity, any value over t will approach 0, and my area in this case will be a 1/2. So if the limit turns out to be a number, we say that's the area under the curve. If the limit turns out to be infinity, then we say, wait a minute, something's not right. I could also be looking at a graph of 2 over x minus 3. So we have a vertical asymptote at x equal 3 and a horizontal asymptote y equals 0. If x equals 0, I will be looking at negative 2 over, so the graph looks something like this. And if I'm looking at the interval from negative infinity to 0, we're trying to find this infinite area. Well, we're going to ignore the limits on the integral. We're going to say, you know what? This is the integral of 2 into x minus 3 cubed dx. Since that's linear and that's a 1, that's simply add 1 to the power and divide by that. Now that was a negative 3, my mistake. So that's going to be add 1 to the power and divide by that. So that integral is going to equal negative 1 over x minus 3 squared. Now I'm going to say, let's evaluate at t to 0 and take the limit as t approaches, in this case, negative infinity. That's going to be the limit as t approaches negative infinity. Plug the 0 in, negative 1 over negative 3 squared, minus, plug in the t in, that would be 1 over t minus 3 squared. That's a plus. As t approaches infinity, this right here will approach 0. Any quantity over t, as the denominator get bigger or smaller, that's going to approach 0. And whether you say it approaches positive 0 or negative 0, that's unique. That's the same thing. So I'm left with negative 1 over 9, and that would be the area. And the reason it's negative, it's because this is below the x-axis. So the integral pretty much tells you if the function is negative, it gives you the negative value, and if it's positive, it gives you the positive value. Next problem up, I'm integrating this. Again, we need to glance at the graph. X over x squared plus 1. Well, this has no vertical asymptotes. That's a graph that looks like this. Now keep in mind, you really don't need the graphs. I'm just showing you what you're doing. I'm running this from 2 to infinity. So pretty much we're trying to find that. Again, the graph is not part of the problem, by the way. So here, I could say, well, let's integrate this. This is a u sub. Let u equal the denominator. du is 2x dx. So this is the integral. Again, leave the limits of the integration. This way you don't have to drag the limit with you until the last step. That's u squared. And this is, oops, it didn't register. Here we go. This is du with a 1/2. So I'll take the 1/2 up front and a du there. That's really u to the negative 2. So that is 1/2. Add 1 to the power, divide by that. That is -1/2, and u was x squared plus 2, evaluated from 2 to t, and we take the limit as t approaches infinity. So that is the limit as t approaches infinity. If you plug this in, that's -1/2 into t squared plus 1 minus -1/2. If you put the 2 in, that's 4 plus 2, that's a 6. So again, this approaches 0, and you're left with a positive 1/12. So if I get a finite number, I say, hey, this limit exists, and there it is. And if I get something that's not finite, like part D, if I want to integrate this, again, we're not going to look at the graph. The graph is not part of the problem. I was just showing you how this works. But this is going to be the integral of x to the -1/2 dx. Add 1 to the power, divide by that. That is twice the square root of x, evaluated from 1 to t, taking the limit as t approaches infinity. That's the limit as t approaches infinity of twice the square root of t minus twice the square root of 1. Well, in this case, that approaches infinity. So here we say it does not exist for this specific problem. And just to demonstrate really quickly, this graph really looks like this. In this case, this area happened to be infinite. So the rest, again, the graph is not part of the problem, but it helps to graph it so you could see what region they're talking about. You could just go by the given information. Here, find the area of the given region. 2 divided by x to the 1/5. Well, that also looks like this, right? And we're running from 1, the x-axis, and to the right of 1. We're trying to find this area. Well, area is going to be the integral from 1, because we're running on 1, and we're going to run to infinity, of twice x to the -5/2 dx. That's going to be 2, add 1 to the power, that's -3/2, divide by that, that's multiplying by the reciprocal. So we're looking at a -4/3, the square root of x cubed, evaluated from 1 to t, taking the limit as t approaches infinity. And that's what we're going to do on every problem. -4/3, plug that in, that is 1 over the square root of t cubed, minus 1 over 1 cubed under the radical. This will approach 0, and I'm left with negative times a negative, which is a positive. 4/3 times 1, and that's my answer. So if I get a finite value, I say that's the area. And if I get an infinite result, I'll say, you know what, that doesn't exist, because I can't evaluate that. If I look at this problem, well, x equal -1 is a vertical asymptote, horizontal asymptote, y equals 0. When x equals 0, y equal 1. So the graph looks like this. And I'm trying to find the coordinate axis, that's the x and the y. An area in the first quadrant, they're talking about this region. So here, I'm going to say area equal the integral from 0 to infinity of 1 over x plus 1 squared dx. I integrate that. That's the integral of x plus 1 to the -2. Add 1 to the power. Divide by that. You could use a u sub, but the same thing. And now I'm going to say it's -1 over x plus 1, evaluated from 0 to t, taking the limit as t approaches infinity. And that would be the limit as t approaches infinity of -1 over t plus 1 minus -1 over 1. Well, this approaches 0. I'm left with negative times a negative, which is a positive 1, and there's my area. So again, improper because we're looking at a value that is not a finite number, and we're not used to that. Normally we run this from an actual value to another actual value. Here again, if I look at 2 over, so this has an asymptote at x equal 2. Y equals 0. When x equals 0, I'm looking at 2 over 4, which is 1/2. So this graph looks like this. And since it's squared, it's symmetric. There you go. And we want to figure this out between the coordinates again. Those are the coordinates. In the second quadrant, they're talking about this area. Well, that area would be the integral from -infinity to 0 of twice x minus 2 to the -2 dx. Again, those are linear. That would be twice x minus 2, add 1 to the power, divide by that. No big secret. That'll be -2 divided by x minus 2 to the 1, evaluated from t to 0, taking the limit as t approaches infinity. So that is the limit as t approaches infinity. Plug the 0 in, that's -2 over -2, right? Minus, plug the t in, -2 over t minus 2. As t approaches infinity, this will approach 0, and you are left with -2 over 2. It's not always a 1, but since in the book they choose problems like this, I'm trying to match. Here we have an asymptote at x equal 3. 1, 2, 3. Y equals 0. When x equals 0, I get positive 1 over 9. So similar graph to what we just did. The graph looks like this. And the problem says go from x equal 3 and the coordinate axis. The coordinate axis are the x and the y. Well, they're talking about this area. Notice that's infinite. So what we're doing, we're trying to integrate from 0 the coordinate axis, because we're limiting that by this axis and this axis. From 0 to 3, 1 over x minus 3. And the reason this is improper, the condition on integration, we wanted the integrand to be continuous. This is not continuous at 3. So we're going to do the same. We're going to ignore the limits on the integral, and we're going to integrate that. That's x minus 3 to the -2 dx. Add 1 to the power. Divide by that. And we're going to evaluate this from 0 to t. We're going to take the limit as t approaches 3. Do you see that we can only approach 3 from the left? So that's the limit as t approaches 3 from the left of what? -1 over t minus 3 minus, put a 0 in, -1 over -3. Well, as t approaches 3 from the left, if I put that in, I'll notice that's going to be infinite. That's going to be 1 over 0. So this is approaching infinity, and here we would say this does not exist. This area turns out to be infinite. And if I look at that problem right there, that will be our last example. Same deal again, the graph helps. You could let me do it without the graph. So if I'm looking at this, well, actually the graph, I could put a number line and I could say, okay, there's 2. And we are looking at area equaling the integral. Now, yeah, the graph is the way to figure out the region. Now, probably on the exam, I'll give you the graph. That shouldn't be an issue. So here, there's an asymptote at x equal 2. And the graph at 0, you are at 1 over. So the graph looks something like this. Oops. And I wanted the coordinate axis. The coordinate axis, we're talking about this area. Again, there's an issue there. At x equal 2, that's undefined. We have a problem. And we're going to run from 0 to 2. Well, the same issue happened. Are we going to ignore the limits on the integral? We're going to say, okay, how are we going to integrate this? We're going to let u equal 2 minus x. du is negative dx. So this is the integral of negative du over square root of u to the 1/2. Add 1 to the power, so that's negative 1/2, right? Add 1 to the power and divide by that. So that is negative twice the square root, and u was 2 minus x. We're going to evaluate that from 0 to t. We're going to take the limit as t approaches 2, because that's where this is not continuous. We could approach 2 only in this case from the left. That is the limit as t approaches 2 from the left of negative twice. Plug that in, the square root of 2 minus t minus square root of 2. If we plug 2 in this case, we notice that's negative twice the square root of 0 minus radical 2. So since that's gone, we are left with 2 radical 2. So if we get a value, that's what the area is. And if it's infinite, we say it does not exist. And that's pretty much it for this section. Again, on your test, I'll provide the graphs. If there's a need, I'll put that on the board, or the test itself. You just have to make sure that you can follow what we're doing and mimic that accordingly. And you have plenty of time to practice that on the home.